So the next one is exercise 10, where we have to find the maximum order of any element in A10. Oh, I forgot to write A10. The alternating group of degree 10, which we already know consists of all the even permutations on 10 symbols. And by now we know how to proceed. We look at all the possible partitions of the integer 10, which are these. And among them, this one, which has only one summand in the sum, 10, is also there. I ran out of space there, so I have written it here. Okay. Now we know what these partitions are for. Each one of them corresponds to a cycle structure of an element in the symmetric group of degree 10, S10. Not A10, I mean, of course we have A10, but first we have to figure out what type of elements or what type of cycle structures actually are permitted in A10. So for S10 we have to consider all the partitions, but then from these partitions we have to decide which ones correspond to even permutations, and we know what that correspondence is. For example, if you look at this partition 4 plus 3 plus 3 of 10, then this corresponds to a product of a 4 cycle, a 3 cycle, and another 3 cycle, and these are all disjoint. That thing is also there. We should not forget that the cycle structure corresponds to a product of disjoint cycles, no matter what they are. So there are 10 symbols, and so here the symbols are not getting repeated. Okay, so now let us see whether this is an even permutation. A 4 cycle, because the number 4 is even, is an odd permutation, and that is because a 4 cycle, we have already seen these things. A 4 cycle can be written as a product of 3 2 cycles. So that number 3 decides that it's an odd permutation. So this is odd, this is even, because 3 is odd, and hence this is even, this is also even. So product of 2 even permutations is even. So this part is even, but this part is odd, and this final product is an odd permutation. So this type of elements are not in A10, and we also know how to calculate their orders. You take the LCM of 4 and 3 and 3, you get 12. Okay, so such elements are not there in A10. Just like that, this partition corresponds to a product of a 2 cycle and 8 1 cycles, but 1 cycles don't matter. We neither write them in our representation as a product of disjoint cycles of a permutation like this, nor do they affect the order in any way, because if you take the LCM in this type of calculations, 1 does not affect anything. Whether you consider 1 or you don't consider 1, it's immaterial. So essentially this is corresponding to a single 2 cycle, which by definition is an odd permutation. So this type of elements also don't belong to A10. This type of elements means that does not mean this sum does not belong to A10. This sum is of course an ordinary sum. It corresponds to a cycle structure of an element. That permutation does not belong to A10. Permutations corresponding to this partition belong to A10, because this partition corresponds to a product of 2 disjoint 2 cycles, which by definition is an even permutation. and the order of such elements will be LCM of 2 and 2, which is 2. You can see one more thing. If you look at this partition, it corresponds to a product of a 5 cycle, a 3 cycle and a 2 cycle. And here if you calculate the order, you get 30, because the numbers 5, 3 and 2 are pairwise co-prime. I don't think you can go higher than that. I feel 30 is the highest possible order that anyone can get, because in the other cases it won't reach 30. The LCM ultimately is going to be less than 30. But the thing is that this partition corresponds to permutations which are not even. Why? Because 5 corresponds to a 5 cycle which is even, fine. 3 corresponds to a 3 cycle which is also even. Even and even give us even. But then one single 2 cycle makes the permutation odd. So this I leave to you. So what you have to do, you have to look at the partitions, decide whether they correspond to an even permutation, and then calculate all the possible orders. From among those orders you choose the highest one, and you will know from your calculation that the highest one comes for that type of permutation. So you can in fact give an example of such an element, a permutation whose order is the highest order in A10. Okay, so this part I leave to you. It's just like the exercises we previously saw. And now we are going to move to the next one. Partitions of 10 are available anywhere wherever you have partitions. Or if you want, you can pause the video and look at all the partitions, take them down. Whatever you wish, you can do. So we now see the next one. Determine whether the following permutations are even or odd. So a number of them are given. 1, 3, 5. In the text, of course, the author is not using commas. However, as we said earlier, to avoid confusion, we are going to use commas. 1, 3, 5, 6. 1, 3, 5, 6, 7. D. 1, 2, 1, 3, 4. And there's one more 3 cycle, 1, 5, 2. and E 1 2 4 3 3 5 2 1. That thing we were saying here, you can now see for yourself. Let's just show why a 3 cycle is actually an even permutation. Okay, if we really calculate this product, let's see if we are actually getting this part. 1 goes to 5, we have to start from this side. Okay, recall that 1 gets mapped onto 5, then 5 gets mapped onto 3, so 1 goes to 3, 1 goes to 3, then 3 is unaffected by this, and then this one maps 3 to 5, so 3 to 5, and then 5 goes to 1, and this does not change 1, so 5 goes to 1. Yes, so this cycle has been written as a product of two cycles, so that number 2 is even, so this is even. This fact is quite fascinating, that although in our in any attempt at writing a permutation as a product of 2 cycles, the product you obtain is not unique. In place of this product, you can get another product also. For example, you can write along with these 2 cycles, you can write 2, 3, 2, 3. Okay, those 2, 2, 3's, the same 2 cycle will give you the identity. So what I am saying is that this is not unique. There are other representations of 1, 3, 5 as products of 2 cycles. The number is also not unique. The number of 2 cycles that appears in those products, that is also not fixed, but the evenness or oddness of the number is fixed. So that decides whether the permutation is even or odd. That is the definition. Then B, since 1, 3, 5, 6 is 6, 5, you start from this side, okay, and you write like this: 6, 5, 6, 3, 6, 1. That is the scheme. The permutation 1, 3, 5, 6 is odd because there are 3 2 cycles. That number 3 is odd. just to be sure that what we are doing is actually is working, we carry out the computation here also. We start from this side. 1 goes to 6, 6 goes to 3, and then 3 is unchanged by this. So 1 goes to 3, 1 goes to 3. 3 is unaffected by this. This one sends 3 to 6, and then this one sends that 6 to 5. So 3 is sent to 5, 3 to 5. Then we start from 5. This does not change 5. This also does not change 5. So 5 passes through these two things unaffected, but then this last one changes 5 to 6. So 5 to 6. And finally, 6 is changed to 1 by this first one from the right side. And then that one is untouched by this 2. So 6 goes to 1. 6 goes to 1. Yes. See 1 3, and you can see what is happening. The cycle, the length of the cycle, if that length is even like this one, the permutation is odd. If the length is odd, here it is 3, the permutation is even. Okay, in fact, you can write the permutation or write the cycle as a product of two cycles. How many two cycles? The length of the original cycle minus 1. Here we have a 3 cycles, so 2 cycles. Here we have a 4 cycles, so 3 2 cycles, like that. So now for part C, we can just simply write, since 1 3 5 6 7 is a 5 cycle it's an even permutation, because it can be written as a product of 4 2 cycles, and that number 4 is even. The first one we don't have to do anything because it is a 2 cycle itself. For this one we write 4 3 4 1. Just like that, for this one we write 2 5 2 1. So how many 2 cycles? 1 2 3 4 5, which is odd. So the permutation is odd, and you can decide this fact without writing these things, just from the lengths of the cycles. This is a 3 cycles, so it's an even permutation, because you see here you have been able to write it as a product of 2 cycles, so that's why it is even. Just like that, this one is also even. Even and even, when you multiply them, that is an even permutation. Why? Because here the number of 2 cycles is even, here also the number of 2 cycles is even. So those two things will give you a representation of this product as a product of 2 cycles. So even plus even is even. Here the number is 2, here also it is 2, and for these two together the number is 4. So that's why when you multiply two even permutations, you again get an even permutation. However, you consider this one also, that makes the number odd. 4 plus 1 5, that's why it is odd. So for the next one we don't do anything, we write like this, since 1 2 4 3 and 3 5 2 1 are both 4 cycles. So both of them are going to be odd. Both of them can be written as a product of 3 2 cycles. So because of that number 3, they are odd. However, together they will give an even permutation. Both are odd permutations. So their product is an even permutation. Why? Let's now see why. You can write this as a product of 3 2 cycles. 3 4 3 2 3 1. Like that, this can also be written as a product of 3 2 cycles. 1 2 1 5 1 3. So because of the oddness of these numbers 3 and 3, individually the cycles are odd. However, when you consider their product, that product can be written like this: a product of 6 2 cycles, and that number 6 is even. So that's why the product is an even permutation. So you can see that if you add, if you multiply 2 odd cycles, not odd cycles, I should not say odd cycles, to even length cycles, they are odd permutations. So the number of 2 cycles in any representation of any one of them is odd. One odd number plus another odd number gives you an even number. 3 plus 3 is 6. So that is the reason for the product to be even. The next exercise is about a property of permutations themselves. Show that a function, or rather when a function from a finite set to itself becomes a permutation. Show that a function from a finite set S to itself is one-to-one if and only if it is onto. and we are concerned with that kind of functions now. For example, the one-to-one onto functions from this set S to itself, such functions give us the symmetric group of degree 3. So in S, I mean, if someone wants to look at such functions, then it's just enough if one sees either one-to-oneness or onto-ness, because the other then automatically is also true for such a function. So this now we have to show. Okay, let f from S to S be a function. First, assume f is onto. Okay. Note that if we take the union of all the inverse images of the elements of S, then that union is contained in S. There are a number of things here to consider. First, recall what an inverse image is. We don't have to recall the notion generally, but only in this case for functions from S to S. F inverse of S is this by definition. It is the set of all elements T in S whose F images are equal to S. If you draw that function diagram, this is your S, this is your S, this is your small s, then this is your F inverse S. The elements, whatever they are in this set, all of them get mapped onto S, and it is the set of precisely those elements that get mapped onto S. So this is the inverse image of S. Okay, and this in general is a set, it's not necessarily a single element. And what we are saying, that the union of all the inverse images is contained in S. That is because each inverse image is by definition contained in S. So their union is also a subset of S. That's what we have written. Also, since S belongs to S belongs to F inverse of F of A. Yes, okay. S belongs to F inverse of F of S for every S belonging to S. We have this inclusion also. Okay, so what is it that we have written in this next line? Here we have written this. We understood this part, we don't need it anymore. S is contained in this. Let us apply the definition of the inverse image to this particular inverse image. It is by definition the set of all elements T in S such that f of T is equal to f of S. Note that this does not necessarily mean that T has to be equal to S. That may not be the case, but other elements, elements other than S can also have the same image as S has under F. And what we are saying, S belongs to this. For that to happen, f of S must be equal to f of S, which however is trivially true. So that's why S belongs to this. Now if you look at this union, here S, small s is varying over all of capital S. So in place of small s, you can in fact think of this also. Corresponding to this, you will get its inverse image, which is this, and that contains the element S. So that means what we are getting is that any element of capital S is inside some such inverse image, particularly inside this inverse image. So that means if we take the union of all the inverse images, that will contain every element of S, and so S is also a subset of the union. And that's why combining these two inclusions, they now become equal. Thus, we have the number of elements in S. Oh, sorry, what? Okay, I am going ahead of myself. S is equal to the union of the inverse, all possible inverse images. Okay, our next statement is this: since distinct inverse images under F are disjoint, the above equation implies the number of elements in S is equal to the sum of the numbers of elements in these inverse images. Okay, now what is this? You see, this equality does not have anything to do with finiteness of S. It is in general true for any function. However, now S is also finite, so we can talk about its number of elements. So what we have here is a situation like this. We are saying that distinct inverse images under F. Under F means this F inverses that we are talking about. if two inverse images are distinct, then they are disjoint, they cannot have any common element. Let's see why. Actually, these are things which we are supposed to know from the theory of functions, but it does not hurt to again recall exactly why these lines are true. Say we have two inverse images, F inverse S and F inverse say T, or let us take S1 and S2 because we used T in a somewhat different, with a somewhat different status. So F inverse S1 and F inverse S2. To express the fact that these inverse images are distinct, you have to take S1 not equal to S2, because otherwise they are the same thing, no? But now you consider you assume that there is something in common, T, that there is in fact an intersection like this. Okay, so this is your F inverse S1 and this one is F inverse S2. Then T belongs to both of them. So by the definition of these inverse images, F of T must be equal to S1, but at the same time, because T belongs to this, F of T must also be equal to S2. Now how can this be when S1 and S2 are different? Because then T has two distinct images under F. F won't be a function at all. Okay, so that is why distinct inverse images are disjoint. And you also get the fact that corresponding to each element in capital S, you are getting a new inverse image. Okay, that fact is also there, which follows from this analysis itself. If you take two distinct elements in S, S1 and S2, here you can see here S1 and S2 are two distinct elements from capital S, then the inverse images are distinct and hence disjoint. They are not just different, but they don't have anything in common. Okay, so what does that tell us? It tells us that these inverse images are actually partitioning the set S into disjoint regions. I should not say use the word partition, because what we can say so far is that the inverse images fill out S totally. That comes from this, because their union is S and their disjointness is, we have just seen. However, are they non-empty, each one of them? If so, then they will form a partition of S. That, however, is not necessarily always the case, but in this case the non-emptiness will be there, and that will come from ontoness. We have assumed that the function f is onto. Have we assumed that the function f is onto? Oh, I rubbed this part, no? So I can't, this is not exactly what is written here. So I can't remember whether I have assumed f to be onto or not. Anyway, if not, now we are going to assume. Okay, so anyway, I have to complete what I am saying. Whether non-empty or not, this splitting of S into disjoint rooms allows us to measure the number of elements in S in this way. You just calculate the individual number of elements in the inverse images, add them up, you get this, and that comes from this thing. Now, because we don't yet know whether these are non-empty or not, some of these inverse images may actually be empty, giving you a 0 in this sum. Note one more thing, that this formula makes sense because S is a finite set. Okay, so this sum is an ordinary sum, this is not an infinite series. Now, we wrote that thing down. Now, first assume that F is, I think we wrote that down, okay, that F is onto. Okay, now we use that fact, since F is onto, any such inverse image will not be empty, and so will have at least one element for every S belonging to S. But now suppose that F is not one-to-one. Then there will be at least one inverse image which has at least two elements. Because then only one-to-oneness will break. No? The situation will be like this. Lack of one-to-oneness means what? You get at least two distinct inputs which give you the same output. Say this is your output is S prime, and here you have two distinct inputs, say S1 and S2. Then in the inverse image of S prime, which will look like this, it may have more, okay, but at least there are two distinct, and they will belong to the inverse image of S prime, because their images under F is S prime, are S prime. So we get this, but now combining all these things, you get a contradiction. And the contradiction is this. This sum will now be violated in this way. But then we have the number of elements in S which is equal to this sum this will be greater than or equal to the number of elements in S plus 1, which is a contradiction. So our supposition is wrong. If you are having some doubt about how exactly this inequality is concluded, it is like this. This part we already have, and because each number of elements in F inverse S, each such number is at least 1, and how many such numbers we will get, as many elements in S we have, that many such numbers we will get. So we will get, because of these inequalities, at least this many ones in from this sum. So all those ones together give us this, plus there is at least one extra, and that extra is coming from here. So that's how we are getting that inequality. Hence, and F must be 1 to 1. Ontoness forces F to be 1 to 1. Conversely, assume F is 1 to 1. Then each inverse image will have at most one element. 1 to 1ness gives you that for every S belonging to S. Some inverse images may be empty, okay, we don't know, but when you have an inverse image that is non-empty, that means you have something, an input for the given element. If this inverse image is non-empty, that means there is something, and on this side you have the output S. So from that something you are getting this F value S, but there cannot be another something distinct from this something, because then 1 to 1ness is being violated. So either there is nothing or there is exactly one element in every inverse image because of 1 to 1ness. Now just like that, suppose F is not onto, then let's write F double prime. Some inverse image must be empty. Okay, there will be some output which is actually not an output at all. It is not coming from any input. The inverse image of such an element will be empty, and so the number of elements in the inverse image will be 0 for some but then what do we get? And this formula, it does not depend on whether F is 1 to 1 or and or onto. It just is in general true. It only depends on the finiteness of S. So we can use this now also in this case. Okay, so now our inequalities are like this. So each such number now is less than or equal to 1, and there is at least one number which is 0. So taking all these things into account, this sum will be less than or equal to the number of elements in S, but because of that one of the terms becoming 0, this. Which is a contradiction. So last supposition is wrong, that is F must be onto, and this completes the solution. Then exercise 13. If you want, you can find other types of solutions also to this exercise. This is, I mean, you don't have to necessarily use an equation like this. You can argue differently. I find this one somewhat neat. This is often the situation in mathematics, that those statements which sound very easy and obvious, you find them difficult to prove mathematically. This is one such situation where, although we understand why a one-to-one function must necessarily be onto, it is somewhat difficult to write logically a proof of that fact. So that's why I brought in this equation. You can, however, without using this equation, argue in a different manner, maybe much more clearly. Anyway, let's just now see the next one. Suppose that alpha is the mapping from a set S to itself. And here is a property enjoyed by alpha. Alpha of x is equal to x. So you apply alpha 2 times, that has the same effect as doing nothing. For all x belonging to S, prove that alpha is a permutation or is one-to-one and onto. This one is easy. Ontoness is almost evident from this equation. For any x belonging to S, we have an element alpha x in S whose alpha image is x. So that means any x in S is an output and the input is alpha of x. So that just means ontoness. Hence, alpha is onto. In terms of inverse images, this alpha x belongs to the inverse image of x under alpha. This relation looks somewhat strange, but you have to understand that this inverse image is a set. It is the set of those elements whose alpha images are equal to x. So because of this, due to this equation, this belongs to alpha of x, alpha inverse of x, and that's why any such inverse image is non-empty, and that is why alpha is onto. For one-to-oneness, let x and y belong to S whose outputs are equal. I mean, the outputs of these corresponding to alpha are equal. Okay, what I said just now, I butchered the language. I should not have said output of these things corresponding to alpha. Ideally, I should say like this: the outputs under the function alpha when the inputs are x and y are equal. Okay, this is our assumption. Then their alpha images are also equal. But that means that the elements input themselves are equal. Hence, alpha is 1 to 1. That is, outputs are equal, then inputs must also be equal. Outputs are equal, there is only one output and different inputs, then the function is not 1 to 1, it's many to 1. Either you do this or you show the contrapositive. You take two different inputs and prove that the outputs are also different. So this is our solution. Exercise 14. Find eight elements in S6, the symmetric group of degree 6, that commute with this permutation. A product of 2 cycles. Do they form a subgroup of S6? since disjoint cycles commute, which is obvious, or you can take two disjoint cycles, that is cycles where there is no common symbol, and convince yourself why they commute. It does not matter which one of them you write first and which one you write after that. The two permutations will have the same effect on any symbol, and that fact comes from disjointness. So since disjoint cycles commute, why am I writing 4? The following 8 permutations commute with I need ink. The identity of course commutes with everything. 1, 2 commutes with this. 1, 2 commutes with this and this because these are disjoint cycles, and 1, 2 of course commutes with itself. So if you write 1, 2 on this side and on this side, they mean the same permutation. Because of a similar reason, 3, 4 and 5, 6 also commute with this one, and then you can take two cycles at a time. And then all of them, of course, together. So how many are we getting? 1, 2, 3, 4, 5, 6, 7, 8. These permutations form a subgroup of S6 because they form a subset that is closed under product of permutations, which you can verify. If for example, if you take the product of 1, 2 with 1, 2, you get the identity because any 2 cycle is its own inverse. If you take the product of 1, 2 and 3, 4, you get this element. If you change the order 3, 4 and 1, 2, they are disjoint cycles of 3, 4, 1, 2 is the same thing as 1 2 3 4. So you get this, you take the product of these two, you get this one. What happens if you take the product of this with itself? You get the identity. You take the product of this one and this one, 1 2 and 1 2 cancel each other, and we are left with 3 4 5 6. In this way you will see that you get a subset of S6 that is closed. But since it is a finite subset, so being closed is enough to be a subgroup. So that's why this is a subgroup. In fact, it turns out to be the normalizer of this 1, 2, because these are all the elements in S6 that commute with 1, 2. Or in fact, we can, why just 1, 2? We can take the element itself. It's also the normalizer of this element, because these are the things that commute with this element. Oh, so what I said right now is not entirely correct. It is the normalizer of this. Okay. That, however, we are not claiming. We are not saying that these are the only elements in S6 which commute with this given element. That is why I am not writing normalizer, because if we can identify this as the normalizer of something, then automatically it is a subgroup. Normalizers are subgroups. So the solution ends here. And let's just see one more, which however we have already gone through the details of this one. Let n be a positive integer. If n is odd, is an n cycle an odd permutation or an even permutation? And like that, if n is even, is an n cycle an odd permutation or an even permutation. So you already know the answer to this. When n is even, the cycle is an odd permutation. When n is odd, the cycle is an even permutation, and we in fact saw why that is so. You can write an n cycle as a product of n minus 1 number of 2 cycles. That's why this thing happens. So I am not going to write a solution here. You can write it for yourself. And let's end things here with group theory. After this, we have another video of Gallian's ring exercises. So let's just now go to that video.